going to start the lecture on nanotechnology in chemical engineering. So today we will discuss about a few characterization techniques, already various nanomaterials that we have prepared. So nanomaterials, nanoparticles, nanofilms, thin films, so that we already have to discuss. So now once that materials have been prepared, so then we have to characterize using various characterization techniques. So already many same themes already have discussed. So today we will discuss SPM, STM, FM and SNOM. So that will be discussed. So that is particularly these methods can be used once the materials have been prepared, its surface morphology, growth of the surface layers of that particular samples that we have prepared. So easily we can analyze with the help of this particular techniques or analytical techniques. So scanning probe microscopes, that is also known as STM, that we will discuss in these two, and AFMs we will discuss, and then a few examples of that materials different image formations topography that will be discussed, and then SNOM, so scanning near field optical microscope, so that will be discussed with few examples. So now we can start the scanning probe microscopes. In this type of microscopes, once we have a thin films on the surface that we have prepared by coatings or any other substrate that be spread over that particular surface in the form of nano films of nanoparticles. So here is sharp tip of the metals that would be used in this particular process or in these instruments that would be scanned through this surface from, let's say, starting from here to here. So across that samples with the raster mode, and once it is at different steps range, that raster will move, and once it is moves and then gives or produced a image of that particular surface of the sample. So in subatomic resolutions, that surface of whatever the image will get with the help of the SPM spectroscopy or microscopy. So that image in this at subatomic levels we can get. So these particular methods actually also known as STMs also. So it was developed by G. Bennings, H. Rurer and E. Ruska, and they have received 1986 Nobel Prize. So other spectroscopic microscopic method also is available, AFM or SNOM. So that also will be discussed. So this much more better. So what are the limitations is there in SPM method or STM method, so that particularly overcomes with the help of this SNOM or FM technology. Okay, so here's you can see the surface. So it is the rough surface. So and then the surface there is a cantilever or the tips, metal tip is there. So once that would move from one particular locations to the another location, so then surface image will get. So the tip, a metal tips, fine metal tips, so its diameters are 10 nanometers approximate. So and the distance means along z directions, the step size that is 0.5 nanometers. So within that level, so it can give the image of that particular surface of that materials we have prepared. Okay, so this metal tips that is obtained, so that also forms by different etching methods in that will be discussed. So in the probe in this SPM, so probe is very important. So material important part of this particular technique. So here it is made of fine metal tips with 10 nanometer diameter, I said. So it's made of silicons or platinum iridium, platinum rhodium, so with diamond films, so that would be coated over the tips. Okay, so that tips usually prepared by etching of a fine metal wire that was taken, and once it is etched, and then after that fine tips would be formed. So that is diameters would be very small, so that is approximate nano range, so 10 to 10 nanometers. So you can say that is prepared. So that if once it is formed or prepared, so then that would be, these tips would be mounted over a piezo drives is there in this particular systems or apparatus. So this piezo drives actually is used to, means objective of this piezo drive to scan the sample surface, so from one point to the another point, and based on that the image will be developed. So this piezo drives, it is made of materials lead, zirconium and titanate. It is known as piezo crystals. So these SPM scans, so that would be, I said, in nanometers and micro levels. So very small surface that may be 0.1, 0.5, 0.10 or 1 nanometer, so 2 nanometers, very small scale. So that elements, so that is present in the surface of that nano coatings or nanofilms or nanomaterials. So in so horizontally that would moves from xy direction, and also the verticals directions, that is the heights of that particular surface. So that is 10 micron up to 10 microns. So verticals, that means surface means xy directions visualize vertical plane direction, so that surface property can be measured. So here's the raster scan, so that is I said that proofs that will move from one directions to the another directions. So if it start from this, so here it would move with a particular step size. Here this is the step size, you can see. So by that way, this is this way, and then it would move this, and this way it would means finished here. So by that way the surface image we can get with the help of SPM. And the patterns of this raster scan, it's maybe rectangular and step size we can change as per our requirements. And to get a very high resolutions of this image of this with the help of this SPM apparatus scanning from microscope. So then a few things we have to note down. So when the instruments will be operated, so any mechanical vibrations that you have to avoid, means that would disturb the scanning process. Also external magnetic fields or any electrical noise, so that we have to avoid to get a good scan of that image. So therefore we have to needs a anti vibrations platforms as well as properly sealed electronics to that we have to use when that systems will be used for that image collection. So next is the STM, so that image I already have said. So here's in this case also we are able to subatomic resolutions. So here's in this case scanning tunneling microscopes, in this case it is also based on tunneling principle. So here's let's say two different metals, so that we can put a small distance to approximate nanometer range distance. So then they once they are placed very small distance, so they would not means that metals would be theirs and at that level. So when their Fermi levels, when they are not coincide with each other, since the transfer of electrons from one metal to another metals is not possible. So when they are coming to the very close distance, so there is some potential barrier is developed. So that potential barriers we can overcome with the help of some electronics, means if we potentials if you are able to develop, so then this Fermi, this is metals 1 and metals 2 that are placed far distance. So then there is not possibility of movements of electron from one metals to another metal. So hence they are coming very close to 10 nanometers or less than that. So then there is a possibility of transfer of electrons from one metals to the another metals. But when they are very close to each other, so if you don't means want to means put that metals, and after that if we develop some potential at applied voltage, so then these two metals there would be a range of the Fermi levels from one metals to another metals, and then electrons will be moved from one point to the another point. So by that way or these principles we can use to means get the means these principles we can use to get the image of that particular species of the nanomaterials that will form. So here these STMs, that methods may be operate two different modes. One is the constant current mode. So that in constant current mode, so here the current between the tip and the samples remain constant. So here this is the tip and this is the specimens or the samples, you can see in between these two. So the currents remain the constants, and then by scanning of that samples in the raster mode that already have said, so then we can get that image of that particular materials or the surface we can get. Okay, so in second one is that is the constant height mode. So earlier one constant current mode, and this is constant height mode. So here the tip that would be moved from the samples one surface to this one point to the another points, those surface maintains a constant height that may be very nano range. So 0.5 nanometers within that range. So here you can see this is the specimens and the tips. So a constant height that would be maintained, and based on that with the help of tunneling current, so the surface profiles or the image that would be generated. So either way we can either constant height mode or constant current mode. So with the way we can get that image, okay, so of that particular specimen. So here's one two examples you can see. So here's the growing of metals, alloys and multi-layers, so on different substrates that have been studied. So here the growth process, morphology and the structures that depends on the roughness of that evaluations during the growth, potential impurity that incorporations in different systems. So systems it will be different. So here you can see an image that is gold surface. So that means after that the same surface liftings or reconstructions, so then the image is different. Here this is image, so here's this image and this image, here's the gold particles that was growth at different levels. So then the surface morphology also changes. So here's the growth is 2 layers in this particular here's, and when the golds or silvers layers that was dispersed over the surface 40 layers, this is 40 layers growth and this is 2 layers growth. So here the surface means image you can see that would be different. So means depending upon different growth layers, so the image would be different. So that has been this type of information so you can get, okay. So then is the AFM, so that is atomic force microscope, so that would give surface topography of the sample. So I said that the surface films, let's say we have formed, so here's the nanomaterials that would be dispersed over the surface. So surface is not uniform, so means surface means different uneven surface may form, so that we can see with the help of this atomic force microscope. So here you can see here is also one tip is there, so metal tip is there and the sample surface is there. So in this technique, so we can develop that image of that particular surface also in atomic scales or nanoscales, so that we can get that particular image of that particular surface of that material, so that we are going to start or we have interest, so that materials we can characterize with the help of this atomic force microscopes also. So here is also that means a tip is there, metal tips, here lasers will be fall over there, and then what are the lights will be reflected, so that will be collected, and with that we can get this type of image. So depending upon the intensity of the lights at different moments, so intensity will be changes once it is moved from one particular point to the another particular point. So in this particular AFM, so in STM there is some limitations, so and for that AFM is much more useful. So here's in this case STMs, so the samples must be conductor or at least semiconductor. So in case of the AFMs it is records any type of samples we can analyze with the help of this, okay. So here's some theories is there, so we are not going to discuss that. So AFM, so there are 3 different mode also we can means this particular systems may operate. So here contact modes, non-contact mode and tapping modes. In contact mode the tips, metal tips that I said, and with that the sample surface will be in contact, and then once the tips will move from one point to the another point, so we can get that image. So in this case the resolutions would be much more better when it is contact mode, tip and the samples will be in contact mode, so then we can get much more better resolutions or of that particular samples image, okay. And non-contact mode, that is also tip that would move from one point to the another point, but with that samples there is no contact, there is some gaps or distance, small distance that would be maintained throughout. So in this process also we can get a particular image of that particular surface or nanomaterials, nanofilms, thin films we can get. So in this process the samples should not be damaged, and in tapping modes, that is in between, so combinations of contact and non-contacting modes. So in this process also we can get that AFM image. So here few examples we are going to show. Here AFM image of cobalt borate catalyst, so that was taken or prepared with the help of cobalt precursor, that may be cobalt chloride or cobalt nitrate that was taken, and then sodium borohydrates that was used as a reducing reagents, and then so once metal chloride or nitrate react with sodium borohydrate in presence of basic solution, so then cobalt boride that would be deposited, okay. So then these reactions we can control with the help of concentrations of sodium borohydrate concentrations. So here sodium borohydrate concentrations was taken like this, Okay, so at different concentrations it was used and cobalt brite sample was prepared, and then the AFM image of individuals materials that was prepared after precipitations of the cobalt brite. So here's different image, you can see the AFM image, this when concentrations was very low, and then when concentration was 0.2 mole per liter was maintained, and then 0.4 and then 0.6 high concentrations we have maintained. So here you can see the images, it is different. So when concentration C3 means 0.4 was taken mole per liters of sodium boride. So mountain like topography, so you can see that have been formed. So means depending upon sample or reagent concentrations, the surface where cobalt boride is deposited, that would be different surface means morphology that has been developed. Okay. So using that, so we can means with the help of this image AFM image of that particular material, so we can analyze different type of vacancies, dislocations, grain boundaries or phase boundaries that is present the materials that we have prepared. So different properties we can characterize of that materials with the help of these structures. Similarly, another example is molybdenum sulfate that was used means for different hydrogen evolutions reactions. So in strong acid conditions, when molybdenum sulfide was taken and hydrogen evolution reactions there, that materials was applied, and after that, so the materials means after keeping it for long term for hydrogen evolution reactions in presence of strong acids, so the structures you can see, that is nano flower film surface that has been formed. So or nanoplatelets like of surface film formations is there. So this type of means study also we can see means before reactions or after reactions the surface changes of that particular materials we can see. Okay, so here another example is the AFM image of catalytic CVD graphene, so that on silicon dioxide. So here silicon dioxide that was taken, so that graphene was deposited. So and so with the help of this AFM image also the structures or depositions of the graphenes over that surface, so we can see. So this is another example is TiO2 thin films that was formed, and the image that was taken with the help of AFM microscope. So here you can see different type of structures means surfaces uneven, and it is forms like that. So next is the scanning probe microscopes. So it probes the electromagnetic fields near at the surface. So with the help of STMs and AFMs we can get that image. So here's optical image at the same times topography of the surface. With the help of AFM we can get the topography. So here with the help of SNOMs we can get topography as well as optical image of that materials that we are going to start or we can going to study. Okay, so this we can see in near field scanning optical microscope, that actually I said already imaging techniques bridge the powerful AFMs with optical fluorescence microscopies and gives the opticals image beyond the diffractions limits. So topography of that materials at the same time optical image both simultaneously we can get with this help of this SNOM microscopes. Okay, it is much better than AFMs. Okay, so here the basic principles of SNOM so that we are going to discuss. So here's in whatever the materials we prepare, so the surface topography or surface we can get in the forms of image. So here the detectors is kept a very molecular atomic level, so but very large distance, that distance is 5 mm as compared to the wavelength of the visible light that would be used, that is 500 nanometers. So means samples to the detector distance, samples and detectors, so distance, so that is very small distance, so or very means as compared to this very large distance, that is 5 mm within that distance. So here in this case actually when some light will be fall over the surface of the materials, so then that light that would leave from that surface of that particles, so that would be means reflected lights that is coming out from that surface of the light that would illuminate the objects and that has two different component. One is evanescent and another is propagating. Two different mode of the components are present. So this evanescent mode or evanescent beam, that is called near fields, whence that would be disturbed and it affects the far fields. So far fields and near fields both are present. So if we disturbs in the near fields, so then as well as same times far field will be disturbed, and based on that the image will gets means over the surface, so that we can gets. Okay, so here I said that electromagnetic fields radiations that would be from the surface we can get. So that would be electron currents and the charge density that is present inside of this object. So charge density and electron currents both that would be induced. Okay, so here you can see here this is the near field lights and this is far field that is scattering from the top or at the tips, and this is the surface, black one is the surface of the sample. So from here also means from the surface or at the from the tips, so both the place. So far field that would be scattering from the surface, and blue one that is the near field, actually these blue ones. So once here you can see the surface is rough surface. So when the tip would move from one point to the another point, so the light that would be coming or scattered from the surface, so near field would be disturbed, at the same time far field also will be disturbed. So that techniques would be useful to collect samples image. So that would be here you can see the topographical means surface topography and optical image of these single DILC molecules. So here you can see at the surface nature, so the image that would forms with the help of a SNOM microscope. So that would comes and that we can analyze what different type of surface morphology or surface topography that is forms. Okay, so here is also another example. So 20 nanometers a high gold or palladium that is structures on a silicon wafer. So here's the distance dependence of the near field optical resolution. So depending upon the distance, here the distance or the tips and the surface is 300 nanometers, 100 nanometers, 30 nanometer and 10 nanometers. So if the distance we can vary, so depending upon the resolutions also will changes. So if tip and the surface sample surface distance is far, so then resolutions will not get good. So when the tip and the surface sample surface distance is very close to each other, so close to 10 nanometers in that, so then we can get a good resolutions of that. So here is the examples of here is another example also, AFM SNOM image comparisons of gold nanoparticles embedded in polyimides. So here this one is the AFM image and this is the SNOM image. So both side by sides you can see that was annals at different temperatures, 150, 250, 450 degrees centigrades, and then this is 150, this is 250, and this is I think this one is 450 degrees centigrade. So that sample was annals at different temperatures, and then if we annals or that's materials at different temperatures, the nanoparticle size also will change. So as per the image, so if we collect for image of AFM or SNOM samples of the different annealing materials, and then we can analyze and their properties also we can study. So depending upon the applications where we are applying, so this is means imaging technology, so that we can use to characterize the materials that we are prepared, that is in nanoscale. So many techniques are available. So this means AFM, STM or SNOMs, that also we can use to get that image, and depending upon that materials we have prepared, that image we can analyze, and based on that properties, so that materials will be used in that particular application. So thank you. So today is up to this. Okay.